The universe is full of objects that shine so brightly they can be seen across billions of light-years. But some of its most important objects are almost invisible. They do not announce themselves with a brilliant surface or a familiar glow. They reveal their presence only by bending light, tugging on stars, and disturbing the space around them. These are the dark giants, black holes that drift through the cosmos, sometimes alone, sometimes hidden inside the centers of galaxies. Today, we are following the clues that let astronomers find them, and asking a deeper question: how many black holes are moving through the darkness without anyone knowing? A black hole is not a hole in the ordinary sense. It is a region where matter has been compressed so intensely that gravity changes the geometry of space and time. The boundary around that region is called the event horizon. Cross it, and every possible future path leads inward, even for light. That definition sounds simple, but the objects themselves come in many sizes. Stellar mass black holes form when massive stars exhaust their fuel and collapse. At the opposite extreme are supermassive black holes, weighing millions or billions of suns, anchoring the cores of galaxies. Between these categories may be intermediate mass black holes, the missing links of black hole evolution. Their existence is strongly suspected, but they are difficult to identify. They are too small to dominate a whole galaxy, and often too quiet to produce the luminous disks that make larger black holes easy to spot. The first major clue is motion. When a black hole has a companion star, its gravity can pull material from that star into a hot, rapidly rotating disk. Friction and compression heat the disk until it glows in X-rays. Telescopes may never see the black hole itself, but they can see the violent environment around it. Yet this method finds only a fraction of the population. A black hole can be completely dark if it has no companion, no active disk, and no nearby cloud of gas. In that case, astronomers must watch what it does to the light of objects behind it. This effect is called gravitational lensing. According to general relativity, mass tells spacetime how to curve, and curved spacetime tells light how to travel. A passing black hole can therefore act like an invisible lens, briefly magnifying a distant star as it crosses in front of it. The event may last weeks or months. The background star brightens, reaches a smooth peak, and then fades back to normal. There may be no flash, no explosion, and no visible object between the star and the telescope. Only the shape and duration of the brightening reveal that something massive passed in front. But lensing can be caused by many things, including ordinary stars and planets. To identify a black hole, researchers need more than a brightness curve. They look for an additional signal, astrometric motion, a tiny apparent shift in the position of the background star caused by the lens bending its light. That shift can be smaller than the width of a single pixel in an ordinary image. Space telescopes and long-term surveys are required to measure it. By combining the brightness change with the movement of the star, astronomers can estimate the invisible object's mass. This is one of the most elegant discoveries in modern astronomy. Instead of photographing the object, scientists measure its shadow and the behavior of everything around it. The black hole becomes a silhouette drawn not against a bright screen, but against the fabric of the galaxy itself. The Milky Way may contain hundreds of millions of stellar mass black holes. Most are probably inactive. Their birthplaces are old supernova remnants, but the explosions that create them can also give them powerful kicks. Over millions of years, these black holes wander far from the regions where they were born. Some may orbit the galaxy alone. Others could be passing through the outskirts of the solar neighborhood, separated from us by enormous distances but still influencing the stars around them. There is no reason to imagine a nearby black hole as a cosmic vacuum cleaner. At a safe distance, its gravity is no more mysterious than the gravity of any other object with the same mass. If the Sun were replaced by a black hole of exactly the Sun's mass, Earth would continue to orbit along almost the same path. The planet would freeze because the sunlight would disappear, but it would not suddenly spiral inward. Gravity depends on mass and distance, not on whether that mass has a glowing surface. The real danger begins close to the event horizon. There, tidal forces can become extreme. One side of an object may be pulled much more strongly than the other, stretching it into a long stream. This process has been given a memorable name, spaghettification. Around some black holes, however, the environment is even stranger. Gas spiraling inward can form a disk moving at a significant fraction of the speed of light. Magnetic fields twist through that disk and may launch narrow jets that travel thousands of light-years into intergalactic space. These jets are not simply cosmic fireworks. They can regulate the growth of galaxies by heating surrounding gas and preventing it from cooling into new stars. A black hole that seems small compared with a galaxy can therefore influence the galaxy's entire future. This connection may help explain one of astronomy's biggest puzzles. Supermassive black holes existed surprisingly early in cosmic history, when the universe was still young. Their rapid growth suggests that the first black hole seeds may have formed through several channels, from collapsed massive stars to the direct collapse of enormous clouds of primordial gas. The answer may be written in faint, distant galaxies. Infrared observatories can look through dust and detect the heat from material falling toward a hidden central black hole. But the deeper astronomers look, the more complicated the picture becomes. A bright nucleus can be powered by an active black hole, by intense star formation, or by both at once. That is why the next era of surveys matters. Repeated observations will create time-lapse maps of the sky. Each map will be compared with the next, allowing researchers to find stars that brighten, shift, wobble, or vanish behind invisible lenses. The more patiently we watch, the less empty space becomes. A quiet patch of sky may contain a black hole crossing in front of a distant star, a neutron star orbiting unseen, or a planet bending the light of an even farther world. The cosmos is not static. It is a moving, layered experiment in gravity. There is also a new kind of evidence, gravitational waves. When two black holes orbit one another, they send ripples through spacetime. These ripples carry information about masses, spins, and distances, even when the collision happens in complete darkness. Gravitational wave observatories have opened a window that does not rely on light at all. They are beginning to show that black hole mergers are common, and that some merging objects have properties difficult to explain with the simplest models of stellar evolution. In the future, astronomers hope to connect these signals. A gravitational wave event might be matched with a lensing event, a flare, or a galaxy's changing nucleus. Combining different messengers could reveal not only where black holes are, but how they formed and how they travel through cosmic time. The search is a reminder that seeing is not the only way to know. We know a black hole is there because nearby stars accelerate. We know it can be massive because it bends the path of light. We know it can merge because spacetime itself rings like a struck bell. And yet, every detection raises a larger question. If the black holes we find are merely the visible edge of a hidden population, how much of the universe's structure is being shaped by objects we cannot directly observe? Perhaps millions of dark remnants drift through the Milky Way. Perhaps intermediate mass black holes hide in dense star clusters. Perhaps the earliest galaxies grew around seeds that formed in ways our current theories have not yet imagined. The night sky looks calm because human eyes capture only a narrow slice of reality. Beyond that slice, invisible gravity is constantly rearranging stars, distorting light, and carrying energy across the dark. The universe is not silent. It is leaving clues everywhere. So when you look at a star field, remember that the brightest points are not the whole story. Somewhere between them, an unseen object may be bending the light, guiding the motion, and waiting for a patient observer to notice. The darkest objects in the cosmos are not empty. They are laboratories for gravity, fossils of dead stars, engines of galactic evolution, and signposts toward the earliest chapters of the universe. And the next black hole discovered may be found not by its light, but by the way it makes the darkness move.